Today's topic is really meant as a prelude to tomorrow's lab. So tomorrow's lab is all about trying to work with something called saturation. You guys ready to go? Okay, so I want to introduce, or maybe not introduce, but remind you of a definition that maybe you knew before, maybe you didn't. Actually, no, before I even get to that. We just talked about this. 3 things that affect dissolving. Agitation, temperature. Particle size would be like how much you crush it up, like surface area. There's actually a typo on one of these things here, though. Every year I always don't change it. Maybe it's good, though. Find the typo. How is this wrong? One of these 3 points has something wrong in it. Yep. This should be a decrease in particle size. If you make the particles smaller, then it should be easier to dissolve them. Does that make sense? If you crush something up, it should be easier to dissolve. I mean, that's from a biological point of view. That's why we have teeth. We chew our food to break it into pieces so that in our stomach, it's already been broken up so the acids can dissolve all of the nutrients out that we need. Does that make sense? No. If we put sugar into our coffee, usually the sugar is already ground up. Does that make sense? Sometimes we put it in like a cube, but usually the cube can crush fairly easily. Does that make sense? But if we had it as like one big solid lump, sometimes it takes a long time to kind of break it into pieces. Make sense? So those are the 3 factors. If you stir something, if you increase the temperature, or if you crush it up and make smaller particles. So this could be your surface area if you wanted. Does that make sense so far? Okay, so let's keep talking about dissolving things. Solubility, we've kind of used this word before. Solubility refers to the concentration of a saturated solution. Which then leads to the second definition. Well, what's a saturated solution? So the goal today about saturation is it's a solution where you cannot dissolve any more solutes. I like to use the word it's full. It is so full of solute that it cannot dissolve anymore. And I made this for my grade 10s yesterday. It worked out great because you guys are doing this. This is an overly saturated solution. I don't know if you guys can see this all that well, but there is some white or yellow crystals floating on the bottom. You guys see that from where you're at? If I try to stir this, it becomes very cloudy, and I can stir it as much as I want. But, I mean, once it settles back down again, there's going to be that solid gunk sitting on the bottom. This solution is overly full. Does that make sense? So solubility, then, refers to the concentration of a full solution. Concentration being like an actual number in moles per liter. One of our goals, then, is to find the solubility of different compounds and find out at what number are they considered full. I actually, in the video lesson, I think I mentioned some of the solubilities of the most concentrated acids that I actually have. Do you guys remember like what those numbers would usually be at?
15 to 18.
Yeah, like I have, I think I have concentrated sulfuric at 18 moles per liter. That's about as full as you can make it. And I think my hydrochloric acid is about 15. Generally, if you have a solution that's about 1 mole per liter or higher in terms of how concentrated it is, if that's its solubility, that's quite full in terms of how concentrated. Does that make sense? So from now on, whenever we talk about a solubility, we're actually talking about a number. So just like when you guys were doing calculations earlier, we want to find the number at which a solution becomes full. Okay. We actually have a table in your book that we've been working with in grade 10. We didn't necessarily use this terminology, but the table is this guy right here. You guys remember how to use this table? Well, one of the things that I always gloss over in grade 10, but I want to talk about in grade 11, is there's a couple of numbers right here. And I've never mentioned those before. We just kind of skip those numbers and just are like, no, whatever. But the solubility is a number. And we've discovered that most solutions, they either have a very high solubility, meaning that they can be like 1 or 2 or 15 or 18 moles per liter. That's how full they can possibly be. Or they have a very low solubility, meaning it's less than 0.1 moles per liter. There are actually very few solutions that are like their maximum fullness is actually at 0.1 moles per liter. It's usually well above that or well below that. And so that seems to be the threshold that we use when we use this table here. I'm just going to go back to the notes we have here. If a solution has a low solubility number, it means that if you were to, like, say, add some solution to the water here, will all of it dissolve? No. And what you're going to get is a solution that looks like this one right here, where hopefully you can see it's already settled down to the bottom, right? You get a bunch of crap in the bottom. Do you guys know what we call that solid stuff in the bottom? Have I used that word before? We call it a precipitate. Do you guys know that word? Oh, here it is. I wrote it right there. A precipitate. If a solution is so full that it's like over full, and there's like extra solid crystals in the bottom, that's known as a precipitate. Like, for example, if you make iced tea, and like you go crazy with the iced tea crystals, and you just keep pouring it in there to the point where like it's a glass of diabetes instead of iced tea. I made that joke on my video. And there's like crystals in the bottom. That's called a precipitate. Does that make sense? If it has a very high solubility, usually it means that everything dissolves, and there are very few that are actually near that mark. Does that make sense so far? Okay. Often what we try to do then, and this is actually the point of our lab tomorrow, is we want to try to figure out how soluble different compounds are. So we actually want to try to find that number. In order to find that number, usually what you do then is you put some solid stuff in and you stir it up. And if it keeps dissolving, add more. Stir it up. Keeps dissolving, add more. Stir it up. Eventually, you're going to reach a point, though, where it won't dissolve and you'll get some solid stuff on the bottom. Does that make sense? In that case, I would say that it is over its saturation point. It's over its capacity. We then try to sometimes plot these things on graphs, because if you increase the temperature, you should be able to increase how much you can dissolve. Remember back from this first slide here? If you want to make something dissolve better, one of the ways you can do is to stir it. But we can't be stirring things for forever. Like, at some point, we got to stop stirring. Does that make sense? Another thing we could do is we could grind it up into small pieces. But at some point, that's kind of as good as it can get, too. But one thing we can control is we can always add more temperature. We can heat things up hotter and hotter and hotter. And so what we can do then is plot on a graph. On one axis, we plot how soluble it is. And on the other axis, we plot how much temperature there is. And without fail, all of these graphs go upwards. They all have some sort of slope, where as you increase temperature, solubility also increases. Tomorrow, what we're going to do is we're going to try to plot this graph right here, the KNO3 graph. That makes sense? And hopefully it will look something like this graph out of your notes right here does. So what we're going to do in our lab is we're going to see how much solute we can dissolve at 20 degrees Celsius. And then we're going to see how much we can dissolve at 40 degrees Celsius, and how much at 60 degrees Celsius. And hopefully we'll get a nice smooth graph. I mentioned before you guys went on your break, one of our goals then of a lab was we have to have a purpose, right? The purpose of tomorrow's lab is to create a solubility curve. How will we know whether our lab was successful? Well, the lab will be successful if the graph you make looks like this. Makes sense? If the graph that you eventually make, for some reason, let's say your graph looks like that. Is that what we would expect? I'd say no, then our lab was unsuccessful. But if the graph that you make looks like this, then yes, the lab will be successful. Does that make sense? So we'll do more of that tomorrow. Typically what we can do is we can actually look up solubilities. There's actually a big book, a handbook for chemistry and physics, that has all sorts of different data numbers in it. I have one. It looks like this. Like it is thick. And basically it's just tables upon tables of data. So usually we can just look this stuff up. But we'll often try to do a lab to confirm that whatever the data is in here or on that graph is what we also get doing an experiment. One of the analogies I like to give to solubility is like a governor on a car. Does anybody know what a governor on a car is? Who knows what a governor on a car is? No one wants to do it. Okay, so most cars have a mechanism on them that makes it so that the car cannot go past a certain speed. Like, for example, my car, the speedometer goes up to like 240 kilometers an hour. But my car does not go 240 kilometers an hour. It's not capable of doing it. There's a mechanism inside the car that makes it so that at a certain speed, no more fuel goes to the engine so that it can't go that fast. Does that make sense? Like it's a... Yes. You've ever heard that phrase before?
Yeah.
Yeah. It means that like your car cannot just keep speeding up until it reaches 500 kilometers an hour, because that would be crazily unsafe. Does that make sense? So most cars, I think all cars should by law have one, and I'd say most of them probably happen at, I don't know, 170 or 80 or something. I don't know. Depends on the make and model, right? If that concept of like an uppermost speed limit makes sense, it's the same thing for solutions. There is a capacity to how fast you can go in your car. There's also a capacity to how much solid I can keep pouring into a solution and stir before it no longer dissolves anymore. What happens again when things are dissolved? Well, that's where this picture here I like. The analogy of you guys are a bunch of grade 11 students, and if I put you into a classroom with 1 million kindergarten kids, you're going to get ripped apart. Does that make sense? You and you and you and you and you probably will not be able to stand next to each other if there are 1 million kindergarten kids ripping at you. Does that make sense? That being said, certain compounds are stronger than others. And so, like you see in this diagram I've got right here, this solution is over capacity because all of these waters are being used, and these waters are being used, and these ones are being used. All of the water molecules have ripped away as much as they were able to, but was there actually enough water molecules to rip everybody apart? No, I guess there was some left over. Does that make sense? So, in terms of terminology then, if I talk about an undersaturated solution, it means you should be able to add more solute, and it should be able to get ripped apart. An exactly saturated solution means it's exactly at that limit. That makes sense? An overly saturated solution would be this one right here. This one is past its capacity. There is too much solid left in the beaker, and it's going to sit probably on the bottom there. Do those terms make sense? Under, over, and then like exactly saturated means that it's exactly full. This is one of the questions on your lab, so maybe we'll talk about it. Let's say I make this solution here and it's over its saturation point. How do I make it so that this solution becomes exactly saturated? Like I can see that clearly there is some stuff on the bottom here. How can I make it so that this solution is exactly full? Not over full, not under full. Like the Goldilocks, you know, not like too hot, not too cold. How do I make it just right? Yeah, I guess. What was that? That's not a bad idea. I could add some more water and keep stirring. What happens if I accidentally add too much water? So I guess in a way it's almost like we'll add more liquid, add more solid, add more liquid. I'm kind of guessing and checking until I figure it out. There is actually a faster way. That's it. Use a filter. If you want to make a completely saturated solution, do what I did here. Make it so that it's over its capacity. Clearly the water molecules here are being stressed. There's just too much solid in here for them to rip all of them apart. So because there's some left over, use a filter. Filter out the extra stuff, and that should make it exactly saturated. Does that terminology make sense? Awesome. Okay, let's move forward here. Typically, it's a solid. Usually the solute is a solid. But if you guys recall from one of my first slides, solutions don't have to be made with liquids and solids. You can make them with gases and solids, or gases and gases, or liquids and liquids. Okay? So the point I just want to make here is if you have a gas solute, it'll probably bubble away. But most of the time, the solid will just sit on the bottom. And the name we have for that solid, one more time, is called a precipitate. Precipitate. Did you guys know that word before I said it today? Or is that a new word? Okay, so precipitation in like weather refers to rain. But a precipitate in terms of chemistry refers to that solid yellow crap on the bottom of the beaker. Does that make sense? So I'll try to use that word from now on. A precipitate occurs in an overly saturated solution. It's past its capacity. So how will you know then whether a solution should be past its capacity or not? Typically, we look at this chart right here. and it will tell us whether we should expect it to dissolve or not. Does that make sense? This chart will usually be the one that helps us figure that out. Okay. Side note here, pop is maybe a counter example to some things. Pop is actually a liquid with bubbles dissolved inside of it. The bubbles being, actually, anybody know? What is dissolved inside of pop that's a gas that makes it fizz up? Carbon dioxide. Yeah, carbon dioxide is dissolved inside of the pop you drink. And that's why, like, when you shake it up and it bubbles, that's carbon dioxide being released from the solution. Okay? The thing I need you guys to know here is that gases have a bit of a different rule to them for some reason. They are actually higher solubility at lower temperatures. So if you actually want to put more gas inside a liquid, you actually need to drop the temperature. Does anybody know why? Okay, what happens to a gas when you heat it? It expands. Will you be able to fit as much gas into something if it needs to take up more room and expand? No. So the best way to pour some more gas into a solution is to actually cool it down, because then the gas will contract and become smaller in space. Does that make sense? So normally heating things up increases solubility, except if it's a gas. Okay. The other thing about gases is if you give them high pressure, that also makes them more soluble. So I just mentioned here, this is why your pop has to be capped and sealed, because when you actually open the cap and you hear it go tss, and it fizzes, you're releasing pressure, and a lot of the gases that were dissolved inside the pop are all bubbling off and escaping. Does that make sense? Because we actually make our pop overly saturated. There's actually so many bubbles shoved inside that they're waiting to burst at the seams and escape. Here's a picture just to represent some of the terminology I've used. So this example right here, I would say is not yet saturated. It's undersaturated. It's unsaturated. We could add more solid to it. If I add too much solid to it, I would actually maybe use the word oversaturated, because there is some solid stuff sitting down here on the bottom. If you can filter this stuff out, then you could actually make it exactly full. There's actually a fourth term I need you guys to know, and it's called supersaturated. This one's kind of fun. The way supersaturated solutions work is that we add some solid to a container, and then we heat it up. And one thing that we know is that when we add temperature, it increases solubility. So we actually add more and more and more solid by adding temperature. Then we rapidly cool it back down again. And what sometimes happens is that the solution is able to hold more solute than it probably should, and it's called supersaturation. It is where somehow it is still dissolved, but it shouldn't be. Does that make sense? You make a supersaturated solution, heat it up. You should be able to dissolve lots of solid. So like if I wanted to make that dissolve, I would just maybe make it boil. That would actually cause all of that solid stuff to dissolve. Then if I rapidly flash froze it, maybe like using liquid nitrogen or I don't know, just a high-powered freezer, what would happen is it wouldn't turn back into solid. It would just stay there in a very, very unstable state. And the cool thing about a supersaturated solution is if you bump it, like if you agitate it even just a little bit, sometimes it'll all of a sudden just miraculously burst into crystals. It's like held on just like the edge of a string, where all of those water molecules are just barely able to keep all the solids apart. And then something happens and then they just turn back into solids. I have a picture of it. I don't actually have the apparatus to make it work, but what would happen in a supersaturated solution is this looks like it's all dissolved. It shouldn't be. There is way too much solid inside this solution. And so if I just tap it with a little rod, you might actually watch things crystallize right in front of you. We're actually going to, on a small scale, do this tomorrow. It won't look quite like this, but tomorrow's goal is we're going to take a test tube and we're going to dump a whole bunch of solid into it and a little bit of water. Like it's going to be like 10 grams or 5 grams of solid. It's going to be a lot of solid and just a tiniest little bit of water. And you're going to try to stir it up and it won't dissolve. Not at all. And then what you're going to do is you're going to put it into a boiling tub of water. And as the temperature increases, more and more of the stuff will dissolve. Does that make sense? And at a certain point, you won't see any more solid at the bottom anymore. Then what you're going to do is you're going to take the solution out of the hot water, and you're going to let it cool back down again. And as it cools back down, you'll actually watch crystals grow on the sides of the beaker, almost like frost forming on your windshield. And what's happening is a supersaturated solution, a solution that has more than it should have, more solid than it's supposed to have, is actually dropping out of that state and reforming a bunch of solid stuff. What we're then going to do is record the temperature at which you start seeing crystals. And that temperature is what goes on the graph you make. Does that make sense? This is one of the reasons why I believe that science needs to be a do rather than just a watch. Because I can show you pictures and I can talk about it, but nothing will be the same as when you actually get a chance to watch it and do it yourself. Does that make sense? So hopefully tomorrow will help solidify this concept. Okay, I just want to focus a bit on the term precipitate for a bit. That's the idea of the solid stuff you make. So I could ask you a few questions on this. Here's an example. Let's say we took copper 2 sulfate and sodium sulfide and we mixed them. My question would be, what would the precipitate be? So what is copper 2 sulfate? What's its formula? CuSO4. Would I expect this to have high or low solubility? How would I know? Let's go to the chart. So I have one that's kind of similar to one you guys have here. SO4, where does copper fit on this chart? Top column. I would expect it to have some fairly high solubility. So chances are, unless I really jam-pack my solution full, it probably should be aqueous. Does that make sense? Then we need sodium sulfide. Anybody know what that is? Na is sodium. What does sulfide imply? Just a single S. You only 2 of them. If memory serves correct, you guys don't have a column in your data booklet for sulfurol on its own, do you? Like in here, is there an S2- in your data booklet? Okay. I have information for you I need to add to your data booklet. I just need to find where I left it. It's an old data booklet. They change like the official data booklets you work with every couple of years, and for some reason, I have the 2009 edition. What edition did I give you guys? Okay, so between the 2009 and the 2010 editions, they changed the data booklet, and they took a column out of this table. I don't know why they removed it, but add an extra column into this table. S2- is soluble with lithium, magnesium, and calcium. And that's it. Most is in the bottom category. Does that make sense? So I have an extra column in my old data booklet, that's why it's blue. You can see I wrote all over this thing. But I save it every year because I always know that they never give you the sulfur column. So that's lithium, that's magnesium, and calcium. So would sodium and sulfide be solid or aqueous then? That's magnesium, Mg.
Is it Mg3?
2+, Mg 2+. So I'd expect that to be solid then. Okay, what forms then? What sort of reaction forms? What do we call this kind of reaction? Double replacement? Does that make sense? Na2SO4 is probably aqueous still. We just did that sulfur column. Sulfur was only aqueous if it was with, what was it, magnesium, sodium, magnesium, lithium, and calcium, I think it was. So this guy would be sulfur. So the question was, what is the precipitate that forms? This is the precipitate that forms. Does that make sense as a way I could ask you a question on this stuff? Usually it involves your data booklet. It may involve working with reactions and knowing double replacement, single replacement. Let me put that up higher. Any questions? Let's try some more examples. Let's say I gave you HCl and NaOH. What would we expect the products to be then? Na would go with Cl. Solid or aqueous? You guys have a table nearby? NaCl. Here's Cl. Where does sodium fall? Top category. So that means it should have a high solubility value. So it probably should be aqueous. I would not expect any solid precipitate then. At least not from the NaCl. Where was it? What's the other product going to be? Water. That one's probably liquid. Let's try the second one though. What if I give you H2SO4 and CaOH2? Or a wasp come in there again? Let me open the window. This is going to make water. The other thing it's going to make is calcium sulfate. Well, water is a liquid. What happens when the calcium goes with the sulfate, though? So I'm going to skip back here. Here's your sulfate column. See how calcium's in the bottom row? You guys know how to use this table? Okay, good. So calcium sulfate would be solid. So I would expect in this particular example then, this one should have a precipitate. This guy right here, I would expect in the beaker, I would expect some solidy sludge in the bottom. Does that make sense? And the solid sludge in the bottom would be that calcium sulfate, which we would call the precipitate. So far, so good? Last concept then, then I'm done. Have you guys ever heard the term equilibrium before? Are you guys in bio right now? Okay, bio, it comes up in bio sometimes. The term equilibrium kind of refers to a concept of being in balance. If something is in equilibrium, everything's in balance. Okay. What was that? They don't actually have to be from a chemistry point of view, but I mean, equal is a major concept though. Okay. What's happening in this solution right here? This is an oversaturated solution. I know that because there's a whole bunch of crap on the bottom. Does that make sense? But this is not a static solution. Do you guys know the term static? Static would mean stationary, non-moving. There is actually stuff happening inside here at a microscopic level. That's why we call this dynamic. There's actually things occurring. What is happening is this solid stuff, some of them are getting ripped apart by water molecules. However, other water molecules are letting go of the stuff that they had ripped apart and are reforming solid. And so what's actually happening is there's a cycle happening inside this beaker that we cannot see because it's at a microscopic level. But some of the solid precipitate is breaking into pieces. But for that to happen, some of the other pieces are actually reforming solids. Does that make sense at all? Maybe I can diagram this here. It looks like there's just solid stuff sitting in the bottom. But if we actually could see with a microscope, what's actually happening is some of this solid stuff is returning into pluses and minuses. However, other pluses and minuses somewhere else are returning into solid stuff. Will you see anything different occurring? Well, no, it's at a microscopic level. but it's actually not static. It's dynamic is the word we use. So sometimes we draw this with double-sided arrows, just to indicate the idea that it's this is turning into this, and this stuff is turning right back into the solid stuff. Does that make sense? So it seems as though that beaker is doing nothing. But actually there's a lot happening in there. Stuff is breaking apart, other stuff is coming back together. I think that's it, right? Is that my last slide? Yeah, I guess it's kind of the same idea here. Say you put a block of salt in water, and it breaks up into pieces. These pieces right here that are stuck together, they don't just sit there the entire time. What will happen is some of these guys will come back in and take their place, and other ones will go out instead. The number of ones that are solid versus the number of ones that are aqueous, that's always the same, but it's not the same ones. So like they can change places. Okay. Here's the section in the textbook in case you want to look this over, but my best recommendation would be for the last few minutes here, take a look at the lab that we're going to do tomorrow, start some of those questions. Maybe you can answer one more question on your assignment that's due. But basically the plan from here on out then is tomorrow we're going to do a lab. Thursday, I believe, is a work day. Then you guys get a long weekend. Our first quiz is Monday. And it's on topics 1 through 4. Does that make sense? Anyone have any questions? All right, cool. So you have like 5 minutes left today. So, I mean, whatever you want to do in this 5 minutes. Just make sure you guys are ready to go right away when we start the lab tomorrow. Lab days are the worst days if you're like taking forever to get going because it really eats into your time to actually do the lab. Does that make sense? So please make sure you're right and ready to go. Grab a lab coat, grab glasses, right at the bell, let's get started. So you have like as much time to do it as possible.